Welcome. In this video, we're going to look at converting equations from rectangular form with x's and y's to polar form with r's and theta. A couple things we want to make sure that we already know. We know that x equals r cosine theta. We know that y equals r sine theta. And we know that x squared plus y squared equals r squared. Well, x squared plus y squared equals r squared. R squared is equal to 9. And if I want to isolate that r is plus or minus the square root of 9 or 3. We can simplify that and just say r equals 3. So you can see my polar equation is much simpler than my rectangular equation. What is r equals 3? Well, maybe from the onset, you notice that x squared plus y squared equals 9 is the form of a circle of radius 3. The square root of 9, r squared is 3. So in this situation, this represents a circle of radius 3. Look at that beautiful, perfect circle. So it goes out in 3 units in every direction, right? But that's all it is. It's a circle centered at the origin of radius 3. Now I can't pull my calculator here up on the whiteboard, but I do want to talk to you about what or how you could graph this on your graphing calculator. If you push the mode button on your TI-84 or whatnot, you'll notice that below where it says radian or degree, which you should feel comfortable switching between, you now see function. PAR is for parametric. There's POL for polar, and SEQ for sequences. So parametric is where we deal with functions x and y that have a separate parameter t. Polar is where we deal with r and theta. And if you go and select polar, then go back up and look at your y equals, tap your y equals button, you'll notice that instead of having y1 and y2 and y3 there, you have r sub 1 and r sub 2. And if you press your variable button, you're going to get thetas in there. So this is a way you can type polar equations. You just need to change your mode to polar. You are used to being in function mode, function y in terms of x. So we're dealing with polar. You may need to switch over. All you got to do is hit the mode button. And I encourage you when you're working on these in your homework to use your calculator to help you graph some of these different shapes. All right, let's do an example where we convert something else. All right, so let's do this one more time. Let's convert the rectangular equation 2x minus 9y plus 3 equals 0 into a polar equation. All right, so that means we want r's and thetas. Well, what is x in terms of r and theta? We already know this. We know what x is. X is r cosine theta. How about y? What is y in terms of r and theta? And that's r sine theta. So then we have plus 3 equals 0. All right, how are we going to deal with this? This doesn't look very nice. This doesn't seem like it would be useful. Well, it is, and you really get to see why it's useful when you get to Calc 3, as I think I've mentioned before. But let's manipulate this a little bit. So I have 2r cosine theta minus 9r sine theta equals negative 3. I will factor an r out on the left. R times 2 cosine theta minus 9 sine theta. It's negative 3. Now I can isolate r. R is negative 3. 2 cosine theta minus 9 sine theta in the denominator. Now, of course, we started with something that is a line, and polar coordinates deal with graphs that are round, circular, or have circular shapes, such as ellipses or circles, or we even talk about cardioids and lemniscates and roses. These are all different kinds of polar graphs. So it doesn't really make sense to rewrite a line in terms of polar coordinates, does it? Let's look at another example. So let's look at one more that you might see in your homework, something that looks like this. So when we start to see these x squareds and y squareds in the same equation, we recognize that it's going to be circular or elliptical. And moving forward, we will learn about different conic sections. And so we'll learn about different equations for ellipses and hyperbolas and circles, etc. And we see this x squared plus y squared. That's kind of an indicator to us that it might be circular in shape. So what does this mean? Well, if we want to convert to polar, that's going to simplify our notation, essentially. So thinking about what we know that x is equal to r cosine theta. So I have r cosine theta squared minus 6. I'm going to turn this x into r cosine theta. We've got two x's there. Plus my y value is going to be r sine theta. So I've got the quantity r sine theta squared is equal to 0. All right, well, let's think about this. I have r squared cosine squared theta minus 6r cosine theta plus r squared sine squared theta is equal to 0. So hopefully you guys are noticing we've got a sine squared plus a cosine squared in here. So this is the same as having r squared times cosine squared theta plus sine squared theta. Don't forget, I still have this minus 6r cosine theta in there. So hopefully this point, you guys are all going, I know what that is, Miss Stein. I know what that is. Cosine squared plus sine squared is equal to 1. And 1 times r squared is just r squared. So I have r squared minus 6r cosine theta is equal to 0. And at this point, I'm going to move this term over to the right side of my equation. I have r squared equals 6r cosine theta. And then, since I know r isn't going to be equal 0 because something of 0 radius wouldn't exist, I can divide on both sides by r. All right, so even though r is a variable, I'm allowed to divide by it because otherwise we would just get a dot at the origin. It doesn't really count for anything. I don't even know if that would be a dot. We digress. So we'll divide everything by r. That's why it's okay to divide by a variable. We get r equals 6 cosine theta. And that's the equation in polar coordinates. So a way to think about this is a radius is equal to 6, and then cosine theta is just moving it over on the x-axis. So if you graph this in polar mode on your calculator, got -3 and +3, you're going to get a nice circle that looks like this, centered at, that would be 3, 0. So let's just look at one more example. For this example, we are presented the equation r minus 9 cosine theta equals 7 sine theta. It's given in polar variables, r and theta. We want this to be in rectangular form, so that means x and y. Now, in a previous example, we divided out an r, and I said that was okay for us to do. But kind of that same logic incites a trick that we're going to think about. So my trick here is that I'm going to multiply both sides of this equation by r. And I can do that because it's an equation. If I did not have an equal sign and this was just an expression, we would not be allowed to scale that up. But because it's a balanced equation, I'm going to multiply on the left by r, which gives me r squared minus 9r cosine theta equals 7r sine theta. Now, what's r squared equal to? We should all recognize that that's x squared plus y squared. I have minus 9. R cosine theta is x. And then I've got my 7. R sine theta is y. And this is fine or acceptable as your final answer. We could use a little bit of algebra to complete the square. We could collect the y's and the x's on both sides as well. I'm going to do that here just so you guys can see what that would look like. And so completing the square, I collected my y's, collected my x's. I added -7 divided by 2 quantity squared. I added that same value. I mean, technically there might need to be a negative in there, but it will turn positive. So that allowed me to complete the square on the left. So I condensed it, and then I applied square root to both sides, plus or minus, which got rid of that square, and I moved the 7/2 over. So this is the rectangular form for this given polar equation, and you can see that this just seems much more unwieldy. Anyhow, at this point, I hope you feel a little bit more comfortable with polar equations. I do want to talk to you and mention that there are a couple different shapes that you might see. You don't need to know these. I just think it's helpful. So one polar graph, r equals 1 minus the sine of theta. This graph's a cardioid. And what that looks like, it's kind of got a little, it's rounded, but it's got a little tiny bit of a heart shape. Cardioid, think about like cardio. We have something like r equals 4 times the cosine of 5 theta. That graph is called a rose. This is actually a 5-petaled rose, which if I am to graph that, I get something that looks, I think it goes like this. Not perfect at this, but about like that. This petal should be a little bit more up like that. It should be tilted, but you get a rose graph. So there are different, you can get different petals or different quantities of petals, but that's a rose. And one of our last ones here is called a lemniscate. Lemniscate is the fancy name for the infinity symbol. If you were to Google lemniscate, it would bring up the infinity symbol. And this graph, I believe we get something that looks like this, and there's 2 little tiny infinity buds in there. These are all really symmetric and nice when you do them in your calculator. I encourage you to just play around, make sure you can use your calculator to create these graphs. Anyhow, that's it for this. So good luck. Have a good day. Talk to you again soon. Email, comment, concerns, any questions, anything. I'm here for you. I'm your friend.